Hello everybody, welcome to Science Explained channel, and we are going to talk about the structure and stability of the atom. So let's first review our previous video named The Atom, the Atomic Theory and Atomic Orbital, where we talk about the atomic structure. The atom has three particles, electron, proton, and neutron. The electron is located in the electrosphere, which determines the atomic volume, while the proton and neutron are located in the nucleus, which is dense and very small, and they determine the mass of the atom. In this animation, we have the lithium-7 with 3 protons, 3 electrons, and 4 neutrons. It has 2 shells, in light blue and blue, where it has 2 electrons in one s orbital and 1 electron in 2s orbital. Remembering our last video, the orbital is a wave function and the electron is a particle wave. That's we are representing here with this type of vibration of the orbitals. And it's not possible to know the position and momentum of the electron at the same time. The number of protons is called atomic number, Z, and the number of neutrons is referred as N. The sum of the number of protons and number of neutrons give the mass number. See that the number of the electrons is not taken into account in the mass number because the mass of the electron is 1,836 times lighter than the mass of the proton and neutron. The isotopes have the same atomic number but different number of neutrons, and each element where Z is less than or equal to 83 has 2 or more stable isotopes. One exception is beryllium. Beryllium-9 is the unique stable isotope of beryllium. The most stable isotope has the highest stability, but each element has several other unstable isotopes. Each isotope has a specific natural abundance, Na, which is determined by its stability. So the most stable isotope has the highest natural abundance. The neutron is the cement of the atom, providing its stability by separating the protons from the repulsive interactions and by interacting with them by means of the strong nuclear force. Let's talk about the atomic mass. The atomic mass, M, is determined by the sum of the mass of each proton and neutron of an atom. The mass of each proton or neutron is given in kilogram or Dalton, dA or U, and 1 Dalton or 1 U has 1.660539 times 10 to the minus 27 kilogram. 1 Dalton is 1/12 the mass of a single carbon-12 at rest, as we can see here in this equation. Then, the atomic mass of each isotope does not have the same value of its corresponding mass number, because the mass of each proton and neutron is not an unit, but 1.00727 U. Then, M is different from A. As we said before, the mass of the proton is 1.00727 U, same for neutron. And the mass of the electron is much smaller than the mass of the proton and neutron, which is 0.00055 U. However, the mass of the electron is added to the mass of the proton to give the mass of the hydrogen 1. The mass of the hydrogen 1 is the sum of the mass of proton and the mass of the electron, and it is 1.00783 U, which is close to the mass of the proton. Let's talk about the average atomic mass. An element can be understood as a weighted average population of its stable isotopes. Then, the atomic mass m of an element is the weighted average mass of the atomic masses of its isotopes according to their natural abundances. Then we can see that the atomic mass of an element is actually its average atomic mass. Here we have the equation of the atomic mass of an element. It is the sum of the product of natural abundance in percent of each isotope and the atomic mass of the each isotope divided by 100. Let's talk about some examples of the average atomic mass. For example, the atomic mass of the hydrogen. The hydrogen has 3 isotopes, hydrogen N0, deuterium, N1, and tritium, N2. The hydrogen has the highest natural abundance with 99.98%, and deuterium has only 0.02% of natural abundance. Then, since the tritium is unstable, is radioactive, only the data of the hydrogen and deuterium is taken into account of the equation of the atomic mass of the hydrogen. The Na of each isotope, stable isotope, and the atomic mass of each isotope, given a number very close to the atomic mass of the hydrogen 1. So let's go to the helium. The helium has 2 stable isotopes, helium-3, N1, and helium-4, N2, and there are 7 unstable isotopes with A equal to 2, 5 to 10. And helium-3, it has a much smaller natural abundance compared to the helium-4, but both of them are taken into account to the equation which determines the atomic mass of the helium element. Once again, the value of the helium element, the atomic mass of the helium element, is very close to the atomic mass of the helium-4 due to the greater natural abundance of the helium-4. And the lithium has 2 stable isotopes, lithium-6, N is 3, and lithium-7, N is 4. And there are 9 unstable isotopes, where A is 3 to 5 and 8 to 13. The lithium-6 has 7.59% of natural abundance, while the lithium-7 has 92.31% of the natural abundance. Both of them are stable and go to the equation of the atomic mass of the lithium element, and we see here that the value of the atomic mass of the lithium element is closer to the atomic mass of lithium-7, but not so close when compared to the same value of the atomic mass of the helium and hydrogen with the most stable isotope, hydrogen-1 and helium-4. The boron has 2 stable isotopes, boron-10, where Z is 5, N is 5, and boron-11, N is 6. But there are 13 unstable isotopes of boron, with A ranging from 7 to 9 and from 12 to 21. The natural abundance of the boron 10 is 20% and of the boron 11 is 80%. Both of them are the stable isotopes of the boron. They are taken into account in the equation of the atomic mass of the boron element, and we see that the value of the atomic mass of the boron element is close to the boron 11, but not so close when comparing to hydrogen and helium, due to the small natural abundance of the boron 11 compared to hydrogen 1 and helium 4. So let's talk about the unstable radioactive isotopes. Unstable isotopes have an unstable combination of protons and neutrons, or they have an excess of energy. All unstable isotopes are radioactive because they spontaneously emit radiation. This radiation has three types: the alpha, beta, and gamma radiation. And the unstable isotope undergo a type of decay, radioactive decay, that has the same names: alpha decay, beta decay, and gamma decay. The alpha and beta decay changes the unstable isotope into a stable or less unstable new atom because the atomic number changes. It increases or decreases by a unit. And the gamma decay makes the atom release the excess of the energy, but there is no change of the atom itself. The unstable isotope is called radioactive isotope, radioisotope, or radionuclide. All chemical elements have an unstable isotope, and most of the largest elements undergo alpha decay. The alpha decay is the emission of helium-4 nucleus. For example, uranium-238 breaks into thorium-234 and helium nucleus. The beta decay has two forms. The first, the emission of a high-energy electron from the nucleus when a neutron becomes a proton, increasing the atomic number by 1, and is called negative beta or beta minus. And second, the emission of positron, a type of a positive electron, when a proton becomes a neutron, decreasing the atomic number by 1, and it's called positive beta or beta plus. For example, of beta minus, we have the lithium 8 lithium 8 breaks into beryllium 8, where the Z goes from 3 to 4 and emits an electron. This is the example of this animation. We see the neutron, unstable neutron, becoming a proton and emitting a high energy electron. And unstable of the beta plus, sodium 22, Z11 breaks into neon 22 and Z10. We see that the atomic number decreases by a unit and it emits a positron. The gamma rays is a type of electromagnetic radiation of the highest energy, and they are emitted in nuclear decay reactions, and also when excited, radioactive atom loses its energy. Let's talk about the unstable isotopes. Carbon atom Z6 has two stable isotopes, C12 and C13. The C14 has a beta minus decay to nitrogen 14. And the most stable isotope is C12 with Na greater than 98% and has a ratio N over Z 6/6 equal to 1. Nitrogen atom Z7 has two stable isotopes as well, N14 and 15. The most stable isotope is N14 with Na greater than 99% and has a ratio N over Z 7/7 equal to 1. Oxygen atom Z8 has three stable isotopes, O16, O17, and O18. The most stable isotope, O16, Na greater than 99% has the ratio N over Z and 8 over 8 equal to 1. All of them, these three examples have the ratio N over Z equal to 1. But this is not it's not the case for all the stable isotopes. For example, boron atom Z5 has two stable isotopes, B10 and B11, but the most stable isotope, B11, with Na 80%, has the ratio N over Z 6 over 5, higher than a unit. Fluorine as well has Z9, has two stable isotopes, F18 and F19. The most stable isotope is F19, and it has nearly 100% of natural abundance. Its ratio N over Z is 10 over 9, which is higher than 1. The same occurs for the lithium-7. So there is not a unique rule to determine the most stable isotope of an element. Simple rules for the unstable isotope. These rules were given by Mark Campbell in Journal of Chemical Education in 1995, and the accuracy of his rules is 95% according to him. The exceptions we found are radioactive isotopes of carbon, nitrogen, and some isotopes of beryllium, etc. There are basically three rules. Rule number 1, for ratios N over Z, even over odd, where it has 50 stable isotopes, or odd over even, which has 53 stable isotopes, if the mass number A of the isotope is different by more than 1 U from the rounded average atomic mass of the element, the isotope is unstable. Rule number 2, for ratios N over Z, even over even, which has 157 stable isotopes, if the mass number of the isotope is different by more than 3 U from the rounded average atomic mass of the element, the isotope is unstable. Rule number 3, for ratios N over Z, odd over odd, only 4 are stable isotopes: deuterium, lithium 6, boron 10, and nitrogen 14. That is the first 4 odd Z of the periodic table. All other odd over odd ratios are unstable. And all nuclides with Z greater than 83 are radioactive. Let's give some examples of the prediction of the unstable isotopes. Note that M here is the rounded average atomic number of the corresponding element. Boron 12, Z5, N7, it has a ratio N over Z, odd over odd ratio. It follows the rule number 3, and it is radioactive. Boron 13, Z5, N8, A13, it has a rounded atomic mass 11. It has a ratio N over Z, even over odd ratio, where the modulus A minus M is 2, and it follows rule number 1, and it is radioactive. Lithium 5, Z3, N2, A5, M, rounded to 7. It has a N over Z ratio, even over odd ratio, and the modulus of A minus M is 2. It follows rule number 1, and it is radioactive. Lithium 8, Z3, N5, it has a N over Z odd over odd ratio. It follows rule number 3, and it is radioactive. Beryllium 14, Z4, N10, A14, M9, it has a N over Z even over even ratio, and the modulus of A minus M is 5, and it follows the rule number 2, and it is radioactive. So we come to the end. Please visit the site of our book. The link is in the description of this video. The book is called Introductory Organic Chemistry, Hydrocarbons, and Physical Chemistry Approach, a Physical Chemistry Approach. Stay tuned to our next book, Quantum Mechanics and Quantum Chemistry, Detailed Historical, Mathematical, and Computational Approach, by CRC Press 2, and will be published in 222. Please check our previous video called The Atom. The link is in the description in the end of this video. Please subscribe to our channel. Thank you very much for your attention.